in this way. So eventually, you will lose all the pluses, they come to the negative, and then you will have zero charge here and zero charge here. That's what we have to do. So the charge will be decreasing. Okay. Charge on the capacitor will be decreasing. Okay. Yeah.
Where does the charge go? Because it is going.
It will go to the negative.
It's going to the negative.
Yeah.
And at the end, the Q in capacitor will be zero.
Yeah. It will be zero. Yeah.
There is a Q.
I will start with it.
So the charge starts from the positive plate, like already charged, and
Yeah.
then it goes to the negative and
Yeah.
becomes zero?
Yeah. Yeah. So let's say this one is positive 1 coulomb here, and I have negative 1 coulomb here. If I move 1 coulomb, 1 positive 1 coulomb from here, I will be left with 0 coulomb here. And what happens when I add a plus 1 coulomb onto a negative 1 coulomb? It will be 0. Yeah.
So the positive and crossover again?
Like, so this one?
No. The negative the positive went all the way around, it stopped at the negative,
Yeah. You can jump the gap.
because there's no.
There is back. There is, yeah, that's basically a wire that's cut off there. This is, you can't jump this gap. So another hand.
In real life, our capacitors, they don't have vacuum between them, right?
Yeah, dielectric. But dielectric is an insulator also.
Okay, so the charge is still charged.
Still can look, yeah. So, that's the case. So let me ask the first question. dq dt. Is that positive, negative, or zero? Yeah, it's negative. Why is it negative? You're losing charge. Yes, the charge as a function of time is getting less and less. Is that clear? Why it's negative? It's less than zero. The current. Is our current positive or negative? Meaning, is the direction of the current correct?
Yeah.
Yeah, so our current will be positive. The current, in magnitude, it's dq dt. But I would like it to be positive. What do I do? Yes, it's negative. Oh. Because the charge is decreasing, this itself is negative, so I have to put a minus sign to ensure my current is actually positive. Yeah.
So the little here in QDT, that represents the charge of the capacitor.
At the moment, yeah.
And then what is the little Q in that of that?
But that's the charge on the capacitor.
That's all.
Yeah. And Q initial is the charge initial. Yeah.
So this charging is always going to be negative dq dt,
Yeah.
and for charging it's always going to be positive?
Yes.
Okay.
For charging, the current is in the right direction, and the charge is increasing, so dq dt is positive. So, yeah.
Are we talking backwards? We're not having a situation where it flows the other way, right, to have negative on?
You mean switch direction? The current, so we start with it going clockwise and then going counterclockwise? No, DC circuits, the current is always in the same direction. AC is where it flips direction. We don't have AC right
So
now.
this is a DCRC?
This is a DC circuit. The RC refers to having a resistor and a capacitor in your circuit. DC means just the direction of the current doesn't change.
So you know that DC is included, but we do another negative sign in front of it when we say that our current is equal to the negative DT, because we want them to cancel out, and all the charge that the capacitor is using is the positive current that requires it.
No, I want my current to be positive. Because I know the direction of the current is clockwise. Remember, what does it mean to have a negative current? It means
Wrong way.
the direction you assumed is wrong. But I know the direction I'm assuming is right. Okay? And so, and I know the charge is getting less, so this is negative. So I need to be, to put a minus sign to make the current, to ensure that the current is positive. Okay? And now I'm going to apply. What do I apply? Gauss's law? No, not Gauss's law.
Loop rule.
Which law? Not quite. The loop rule. Yes. The loop rule. Okay. Loop rule. Can I have? Yeah. The loop rule will be. Where do I start? Okay. I start here. Okay. I can start here. But. You're going to, I like to start here, so that when you go from here to here, the change is positive.
Okay.
Okay. But the point I was actually trying to make was, it doesn't matter where you start, and it doesn't matter what direction you go, whether clockwise or counterclockwise, because at the end you get zero, the change is zero. But I always like to have a positive change at the beginning. So I start here, and what's the change from here to here? It's the voltage across the capacitor, and it's positive, right? Yeah. So here it is. You said positive Q over C?
Yes.
Okay, Q over C, that's the voltage. And then here, minus IR, good. Equals to 0. Loop is complete. And then move this to the other side. Yeah. Q over RC is equal to I. I divided by R. And then I is, that's where this one comes. You will see the consequence of not having a minus sign there. You will see, if you're off by a minus sign, you see what happens. Minus so again, PQ over Q, this is minus DT over RC. You see how I did that? Divide both sides by DQ and multiply by minus DT. And then what do we do? Good. At t equal to 0, to t, what was the charge at t equal to 0? This one, right? Yeah. And then at a later time, we're just going to borrow little q. So now we need to simplify. This would be natural log, right? And it would be ln of q over capital Q, right? Ln. So q over capital Q. And here you will have minus t over RC. And so do the exponential and then multiply by q naught. So you get little q naught e to the minus t over r.
So little q represents the current charge of the capacitor?
Yes, the charge at the particular time. Yeah.
Oh, and then, okay, so I get that you need your eye, so your eye, if you chose your direction right, should always be a positive. So that's how you have that extra.
Yes. Okay. Yeah. And if we got the, if we got the negative sign wrong, so look at this. You will have a positive exponential, right? What happens to the charge if the exponential is positive? As t goes to infinity, how much charge do you get? Yeah, the charge will just grow to infinite charge, which is obviously wrong. Okay, so that's Q. So let's just write it. Q is how about I? Let's take the derivative of this. Derivative will give you minus 1 over RC, right?
Yeah.
Now, but then have a minus becomes plus. So you just have Q. Then we're going to graph them both. This is T. This is Q. At T equal to 0, Q is Q 0. Right? As T goes to infinity, what happens to the charge? Goes to 0. How about current? What's the initial current? Oh, this is it. You have the RC. Q naught over C is the voltage across the capacitor initially. So you still have that V over R. That's the current. And then as T goes to infinity, what happens to I? Yeah, it should have less current. We're not quite done with that one, so I'm going to talk about it a little more. So Q naught over C is the voltage across the capacitor, right? Initially, Q over C is V. Yeah. So it's V over R. That's the current.
Charge-nya ya, kan dari 0. Oh, that's why. Oh, kapasitor tuh buat apa sih dipakai? Di HP ada kapasitor? Ada. Apa?
Ready for the next thing? It's going to be the same equations, but I want to talk about the energy stored in a capacitor.
Kayak iPhone.
Energy stored in a capacitor.
Cepat sampai 80 sampai 100 Iya. Iya.
You guys see sounds good, right? Are we waiting for a moment?
Kalau kata
So energy stored in a capacitor. What's the energy stored in the capacitor initially?
0.
Capacitor was charged.
Oh.
It had charge Q naught. So how can I express the energy in terms of
Q not V.
Q naught V? And I want in terms of Q and C. 1/2 CV squared, and I don't want the V there. I want just the Q and C. There is one equation.
Q squared over 2C.
Yes. Yes. That's the energy stored in the capacitor initially. What's the energy stored in the capacitor when it's completely discharged? 0. Okay. And the question is, where did the energy go? Right? Energy is conserved. So where did it go? Dissipated to heat.
I just
Yeah,
dissipated.
correct. To heat. Okay. Okay. So all right. So it's dissipated to heat in the resistor. Right? Remember, the resistor consumes energy at a certain rate. What's the power? Let me put here. P is for power. Power.
Iya.
Right? What's the power consumed by the resistor?
Iya.
IV?
Yeah, IV.
Or how about in terms of current and resistance only?
I square R.
I squared R, good. And we want to show that the total energy consumed by the resistor will be equal to this initial energy. That's what we want to show. I squared R. So here is I. This is I. That's the current as a function of time. current is not steady, right? It's decreasing. So I'm going to use that. Again, is the goal clear what I'm trying to do? We had an initial energy in the capacitor. The capacitor would be completely discharged when t goes to infinity. And the question is the power consumed by the resistor from between 0 and infinity actually equal to this? It would be, but we want to double check as an exercise. So we get P. Again, P is power, right? Not momentum, not pressure, it's power. Let's square these things, so we get Q naught squared. I would have R squared on the bottom, but I have an R here, so I just have R on the bottom. And then C squared. And then e to the minus, when you square this, what do you get? E to the
Minus 2t.
twice, yeah. 2t over RC. When you square the exponential, the power is multiplied. So that's the power. And power is the energy consumed per second, right?
Yeah.
It's du dt. That's the energy that's consumed.
Power is energy consumed per second.
Okay. So let's see. So du will be the power times dt. So that's u naught over r c squared. Not u naught squared, yes. Minus 2 t over rc. And then d. Okay. What are we going to do next? Yes, we're going to integrate. So we're going to have this. Here is u. Let's use this color. These are constants. Between 0 and what? When does the capacitor completely discharge?
T.
T? When is that? Yeah, infinite. It takes infinite amount of time. Okay. You get u naught squared over r c squared times this derivative there. You get minus rc over 2, and then e to the minus 2t over rc, right? Between 0 and infinity. Clear? The chain rule, you need to account for it, right? That's why I have the minus RC over 2. RC, one of these C's cancels, and this R cancels. So I get Q squared, Q naught squared, 2C, and there is a minus sign.
It is true. Why do we get this though? At first. Kan bisa sama dengan QVO. Oh, yang kayak sama dengan
Let's
QV
substitute.
QV.
The upper limit, what do you get? Which is? Zero. Minus e to the 0 is 1. So you have this. And so the total energy consumed by this resistor actually adds up, right? So just yeah.
Why would it take the amount of time?
Why would it? Yeah. So when does the current completely go away?
Oh, I guess never.
Yeah, infinite amount of time. Yeah.
Unless it's given on the questions, right? Like the current completely lost at t is equals to 30 seconds. Is it possible? Like
Well, according to this, no.
no?
No.
Oh,
It takes an infinite amount of time. But, I mean, you can be satisfied, you say, when the current is below a certain amount, that's basically zero.
oh.
Right. So,
So like theoretically, like I is so hard to completely.
yes, yeah. So let's say when you lose 99% of the current, then that's essentially zero.
Oh, I see.
Yeah. This chapter is officially done. This is chapter 26. This is not on the exam, but it will be on the quiz that follows the exam. So I'm done with this chapter. Let me pause this.